going to learn about limits at infinity. Okay, so first let's go over some rules. If you can see in A, the limit of c over x to the r as x approaches infinity is 0, and the same is true if x is approaching negative infinity, where r is a positive rational number and c is any real number. So what are we saying here? Well, an example, when we say c over x to the r, if you look at item 1, an example of that might be, for example, 3 over x cubed. So if we take the limit as x approaches either positive or negative infinity of 3 over x cubed, that will be 0. Now, why is that so? Well, if you think about it, the numerator is a constant. Constant is not going to change. The denominator, however, is x to some positive power. And if x is approaching a positive infinity or even negative infinity, that number, that denominator, will grow to be a very large positive or negative number. And if the numerator is not changing but the denominator keeps growing, the fraction as a whole is going to shrink and the limit is essentially going to approach 0. Think about if you had 3/10ths and then 3/1000ths and then 3/1,000,000ths, that fraction is getting very, very small and the limit will be 0. So that's essentially what we're saying. The second rule we want to talk about is in B. This says that if we have a limit of a function as x approaches infinity equal to L, L being our limit, or if we approach negative infinity, same thing, y equals L. That line is basically a horizontal asymptote of our function. For example, we might be referring to the line y equals 1 if our limit is 1. Okay? And we'll show an example where this is the case. So let's do an example. Let's start in A. In this case, x is greater than 0, and we're looking at the limit of our function as x approaches positive infinity. And you can see in item 1, I have our function. So how do we determine what this limit is? Well, if you go to item 2, what we're going to do to the numerator and the denominator of our function is we're going to divide essentially by x. And we choose x because that is the variable with the highest exponent. That's usually a good choice. So since x is, we do have an x squared in the denominator, but remember it's under a radical. So it's really the square root of x squared, which is essentially still x. So we're going to divide by x. And we divide the numerator by x as well as the denominator because we don't want to change our function. Well, dividing the numerator by x works very nicely because if you can see in item 2, the x's are going to cancel where the 2 is, so that's going to leave us with 2. And then when we divide 5 by x, that's the rule we spoke about in the last slide. The limit of 5 over x as x goes to infinity is going to be 0. It's a constant over x to a power. So that goes away. So then in item 3, the numerator is simply 2. Okay, now let's look at the denominator. So if we go back to item 2 in the denominator, we have divided by not x, but the square root of x squared. Why? Because we have a radical, and to divide we need to divide by something that's also underneath a radical. So we can put everything under one radical. And the square root of x squared is x, which is what we divided the numerator by. We have to be consistent in the denominator. Then if you go to item 3, we can now put everything under the radical in the denominator. So 4x squared is divided by x squared, and then 10 is also divided by x squared. Well, when we go to the 4, those x squareds cancel, so we're just left with the square root of 4. And then 10 over x squared is that rule we spoke about earlier. Constant in the numerator and x to some power in the denominator. The limit of that as x approaches infinity is always 0. So that disappears. Now we go to item 4. So we reduce to 2 over square root of 4, which reduces to 1. And then if you take the limit of 1, that's always going to be 1. And that's what we get in item 6. The second example, B, is exactly the same. The only difference is that now we're dealing with x approaching negative infinity, and x is less than 0. When you have this scenario, the main difference between this example and the one we just did is that if you go to item 8, you'll see when we divide, instead of dividing by square root of x squared like we did in the other example, we have to divide by negative square root of x squared. The reason is, well, square root of x squared is always going to have a positive result no matter what x value is, but x is less than 0 in this case, so we need to put a negative in front to compensate for that. And if you go through that process and you go all the way to item 12, you'll see that our limit in this case is going to be -1. So let's see what our graph looks like. If you look at this graph, this is the graph of our function, and you'll see what happens when x approaches both positive and negative infinity. Well, let's go to item 3. If you look at item 3, you'll see I have an arrow, positive infinity. So just pretend you're standing on the graph and walking to the right all the way to positive infinity. What's happening to our graph? Well, it's getting really close to that horizontal red line. That represents our horizontal asymptote. And where does it occur? At the line y equals 1, which is at item 1. And that line is at y equals 1. Why? Because we already determined our limit was 1 when we approach positive infinity. So we have a horizontal asymptote there. Now what happens when we're on our graph and we're walking towards negative infinity? Well, if you go to item 4, you can see I've shown it there. Again, imagine yourself standing on the graph, walking to the left, and heading towards negative infinity. Where is the graph winding up in terms of the y value? It's getting very close to y equals -1, but it never quite gets there. And that represents our horizontal asymptote. And we already determined that the limit as we approached negative infinity was -1. So that indeed is our horizontal asymptote at y equals -1. And that is our study on limits at infinity. Now go practice, practice, and practice some more.